Hello, everyone, and welcome to the last day of electrochemistry. So, today we're going to focus in on a topic that we've brought up a little bit before, and that's going to be how activity relates to electrochemical potentials. So, here we're going to take advantage of a key feature, which is that activity really is telling us about the Gibbs free energy of a non ideal system. And it turns out there's really no better way to measure the Gibbs free energy of a system than to directly measure it through an electrochemical potential. So we're going to essentially take advantage of this by looking at our good old friend, the Nernst equation. So our Nernst equation relates the measured potential of a system to its standard state potential by, again, the reaction quotient. However, one of the things that's worth acknowledging here is that this reaction quotient is really a ratio of chemical activities and not just the simple molalities that we'd wish it to be. However, we can go ahead and split up our reaction quotient into its ideal and its non-ideal components. So our ideal reaction quotient is our good old friend products over reactants, just dealing with the molalities of the system. The um, the activity, the reaction quotient of our activities, however, is specifically dealing about with the ratio of the non-idealities, or again, the ratio of our activity coefficients. So if we really want to know about the non-ideality of a system and its deviations from ideal behavior, this is the value I'm really going to be interested in. So we can go ahead and try and isolate this behavior by, first of all, using natural log laws to split our equation up into a natural log of our ideal and a natural log of our non-ideal behavior. And then what we can do is add our natural log of our activity coefficients to both sides, and then move our potential over here to the right side, and then divide the whole thing by RTNF to get rid of this nasty precursor. And when we do this, what I'm left with is the difference in between my standard state and my measured chemical potential, all over essentially a big unit conversion based on the number of electrons being transferred in this chemical reaction. And then I'm going to essentially subtract out the ideal behavior. So what this means is that I can figure out my activity coefficients if I have one, or the ratio of my activity coefficients if I have multiple activity coefficients present in this Q, simply by knowing the chemical potential of my system, measuring the potential of my reaction, and then simply knowing the molalities of everything that I put into solution. So this is actually a very direct way of trying to determine the non-ideal behavior of a real system. So this is going to be a very powerful way of determining activity coefficients. However, let's be honest, this general expression is a little bit ungrounded. So let's try and relate this more general expression to a real chemical system. So when trying to evaluate chemical behavior, a classic case to try and examine is what's called the Harned cell. So this is actually one of the more simple electrochemical cells, and it's one of the cells that's the most important to determine its behavior, because the Harned cell is literally combining together a standard hydrogen electrode for an anode and using this as the electron source for a silver-silver chloride cathode. And so if I'm able to determine the potential of this reaction, then ta-da, I'm also able to accurately determine the electrochemical potential for silver-silver chloride, which is our practical reference point in most electrochemical reactions. So a very important reaction to have adequately described. So in order to try and describe the system, we're first going to want to examine what our net chemical reaction is. So in this case, our net chemical reaction can be described as essentially combining together hydrogen gas with silver chloride to produce hydrochloric acid and a silver solid. So in this case, we can then generate a reaction quotient, which is going to be the ratio of the activities of products over reactants. Now, here I have to account for one important feature, which is that HCl is actually a strong electrolyte. So in truth, it's going to fall apart into protons and chloride ions. And our only major reactant that's going to show up in a reaction quotient is going to be hydrogen gas, again, raised to the half power because of our 1/2 coefficient. Also, since this is an electrochemical reaction, it is important to point out that I'm going to be transferring one electron from my half hydrogen molecule to the silver metal. So one of the things that is worth acknowledging is that under these conditions, well, hydrogen is going to behave fairly ideally near standard state conditions because 1 bar hydrogen is really no big deal. However, once I get up to 1 molar ions, well, then I have to worry about these activity coefficients not quite being as ideal as I would like. So in this case, I'm going to essentially assume that the hydrogen is going to behave relatively ideally, and I'm going to try and focus in more on the solution, which is a classic trick we like to play. So when we do this, what we end up finding is that our reaction quotient is simply going to be the product of the proton activity and the chloride activity. And then when you combine these two features together, what you'll notice is we can go ahead and split out this behavior into our ideal reaction quotient, at which point I'm going to treat those activities as molalities. And then since I'm buffering my system with HCl and not independent protons and chloride ions, what I can then do is take advantage of the fact that these two molalities should be the same. So my ideal reaction quotient can simply be given as the molality of HCl squared all over standard state molality of, again, 1 molal, which is mostly going to serve to keep my units balanced. However, each of these ions is going to have a mean activity coefficient of HCl. So we are lucky that they're going to share a mean activity coefficient. But since it shows up twice, it means that our reaction quotient of our activity coefficients is going to just be our mean activity coefficient squared. So what I can then do is take advantage of this ideal and non-ideal reaction quotients and throw them into my Nernst equation. And when we do this, we're going to find that our potential is going to again be given by the standard state potential of the silver chloride electrode, and then corrected for by the molality of HCl and the mean activity coefficient for HCl for this molality, because again, our mean activity coefficients do show a concentration dependency, as they'll be near 1 for a molality of 0, and they'll often be much lower for higher concentrations. However, in order to try and make it a little bit easier to isolate and determine what my mean activity coefficient is, what we're going to do is go ahead and pull out our squared term on both the molality and the mean activity coefficients out front to form a coefficient of our natural logs, because who doesn't love our log laws? And then we're going to go ahead and move the natural log of my mean activity coefficient over to the left side and move our measured potential over to the right. And again, making note that here n is going to be 1, and we have this extra 2 factor comes in again from these coefficients. So when we do this, we can then divide the system all by this 2RTF, and we get essentially a modified form of our earlier expression, where I can determine the mean activity coefficient for HCl by using the standard state potential for silver chloride and the measured potential from the actual Harned cell. and then again, correct with the natural log of the um, molality of HCl being used in this case. So when we earlier had all of those activity coefficients that we were um, trying to replicate with our Debye and extended Debye and other forms of other equations, this is really the data we were trying to fit, was real electrochemical data. And again, this is a very powerful technique, as if long as I know the standard state potential, using these measured molalities and measured potentials, I can accurately determine our activity coefficient. And again, in this case for HCl, but you can extend this technique with other modified cells in order to get other other activity coefficients. However, one of the other things that is worth noting is you can kind of inverse this same sort of logic. And then think about, what do I do if I have an electrochemical cell that I don't know my standard state potential of, and I can't just look up in a table? Well, in this case, what I can go ahead and do is take my earlier equation. I'm going to go ahead and move my natural log of the molalities over to the left-hand side while leaving my standard state potential and my activity coefficients on the right-hand side. And then, because it's often easy to look at activity coefficients in a log 10 basis, we're going to essentially convert from log E to log 10 using our natural log of 10 expression that we addressed earlier. So then using this relationship, what I can then say is, well, why do I care about the log of activity coefficients? And it turns out the reason why is because of our good old friend, the Debye-Huckel limiting law. And in this case, we found that the log of an activity coefficient is related to essentially a parameter based on our solvent, the charge of the system, and our ionic strength. Well, in this case, we actually get pretty lucky because our charge for both of our ions is 1. However, I'm going to leave this expression in to show how we can essentially extend this model to different ion pairs. And A will again be constant for any aqueous system. But where we get really lucky is that the only ion present in the system is going to be our HCl. So in this case, because I've got single ion species, my ionic strength is simply going to be the molality of HCl being used, which is going to be a very nice simplifying technique. So this means that under these dilute conditions, which control the Debye-Huckel limiting law, I can essentially relate my potential and concentration to my standard state potential, and again, a longer expression for my standard state conditions. So what I can then do is, using this equation, I can note that this has the general form of a linear equation. So I'm going to know the molality of my HCl, and I'm going to be able to measure my potential. And I'm also going to be able to measure the molality of my HCl, and everything out here is just a constant. Faraday's constant is a constant. A depends only upon the presence of the solvent. Our measurements should be made isothermally, and again, R is the ideal gas constant. So I now have a general linear equation where I can put in various values that I measure for Y and various controlled concentrations for my X, leaving a well-known expression for my slope, and all this leaves me behind with is my good old intercept. So I can then go ahead and fit this data again under low concentration systems to make sure that the Debye-Huckel holds, to determine my standard state potential. So by plotting our modified potential against the square root of our dilute HCl concentration, we can accurately determine standard state potential for, in this case, the silver chloride electrode. But you can also imagine using this same general technique, and again, other similar ion-based cells, try and accurately determine other standard state electrode potentials. So again, this is one way how making use of activities can can help us determine standard state potentials, and sometimes we're not always going to be limited to using standard state potentials to determine activity coefficients. But this really kind of helps show how so many of the features we've been bringing up all semester of activity, Gibbs free energy, can really come together to accurately describe a real chemical system. However, so far we've mostly been focused in on issues of thermodynamics. Next time, we're going to start talking about that very elusive topic, kinetics. Until then, take care.